Okay, so welcome back to this next video in which we are discussing the definition of a vector space. Okay, so we now have completed the definition of a vector space, and we've seen that it's another type of number system. So once again, you start off by creating a set of symbols, and the symbols in this set are going to be called vectors. Okay, and then what you firstly do is define an addition composition law for all of these vectors, so you can add one vector to another, and that addition composition law needs to obey the axioms of an abelian group. Then what you do is create a second composition law, which is going to be a scalar multiplication composition law, and this is where the field becomes important, because this isn't a composition law of elements in the vector space with elements in the vector space. It's a composition law involving elements of the field scalar multiplying elements of the vector space. Okay, and we've now been through the axioms then that scalar multiplication composition table must obey. Okay, so what I now want to do is, if we start off with an abstract field, capital F, how do we actually construct some vector spaces over that field, capital F? That's what I want to ask in this next video. Okay, so we've got some arbitrary field, capital F, and we've seen lots of examples of fields now. We know that the rational numbers are a field, we know that the real numbers are a field, we know that the complex numbers are a field. We've also seen the prime field, so that gives us a brilliant bunch of examples of finite fields. Okay, there are other finite fields beyond just the prime fields, which we haven't seen, but the prime fields are enough for us to have a good intuition for finite fields. Okay, right, so we've got some arbitrary field, capital F here, okay, and I now want to actually construct a vector space over this field, capital F. Well, the absolutely first thing to say is that if I just let the vector space equal an exact replica of the field, then I'm going to be done. I am going to actually get a vector space, i.e. the field is a vector space over itself. Okay, so let me explore this with you in a little bit more detail. So what I'm now going to do is let the set of symbols, the set of vectors, be all the symbols that are in the field. Okay, I'm going to let the addition composition table here be the same as the addition composition table that we already have defined on the field, and we know indeed that will form an abelian group, so this is all looking good. And I'll let the scalar multiplication table of elements of the field with the vector space just be the multiplication table on the field, because after all the elements of my vector space now are the elements of the field. Okay, so it now will just be a table of elements of the field multiplying elements of the field. Okay, so I'll just let that composition table then be the multiplication table that I have on the field. Now let's just make sure then that that multiplication table on the field will then satisfy the axioms that the scalar multiplication table needs to obey. So let's start off with closure here. Okay, well that will be true because whenever I take one element of the field and multiply it by a vector is now an element of the field as well. I will get another element of the field, which of course is my vector space, so indeed it will be closed. So says scalar multiplication does obey closure. Second axiom, associativity. Okay, well now both these elements here, C1 and C2, and the vector, little v, are elements of the field. Okay, because the vector space is just equal to the field, capital F. Okay, so now this scalar multiplication is just multiplication in the field, so this is just three elements of the field multiplied together, and also this is three elements of the field multiplied together. So really this is just equivalent to saying that multiplication in the field multiplication table, must be associative, and indeed we know that it will be associative, and therefore this axiom number 2 here, will be satisfied. Okay, if we're going to let the vector space equal the field itself. Okay, then let's turn our attention on to this third axiom. The multiplicative identity must multiply by any element of the vector space to give that the element of the vector space back again. Well now, v is just some element of the field, okay, because we're letting capital V be the field. Okay, so we're just saying that one must multiply by any element of the field to give that element of the field back again, but of course it does, because 1 is the multiplicative identity in the field multiplication table, so it does multiply by any element of the field to give back that same element of the field again. So that one we can tick off as well. And then the axiom number 4 here, the two distributivities. Okay, so this one first. So C will be an element of the field, and V bar will be elements of the field. So here we'll just have addition will be within the field, because we said that the addition that we were going to use as our vector addition was just going to be addition in the field. So this is effectively just equivalent to saying that multiplication over the field distributes over addition in the field. Okay, so indeed that is true. Then, when we take this one on, C1 and C2 are just elements of the field, V is an element of the field, okay? So what we're doing here is we're just multiplying C1 plus C2 in the field by V, which is in the field, and we want it to be equal to this, okay? Well, this is going to be true because distributivity is true in the field, okay? And commutativity is true in the field as well. So what I'm going to do is I'm going to prove that this is going to be true using the distributive property of multiplication over addition that we've stated for fields and commutativity. Okay, so if I want to prove that C1 plus C2 times V is equal to that, then what I'm going to do is first I'm going to say, okay, because multiplication in the field is commutative, I can swap this around to V times C1 plus C2, and the answer will be exactly the same. Okay, so that's by commutativity of multiplication in the field. Then what I can do is apply distributivity that we saw is an axiom of field theory. Okay, and we can split this into V times C1 plus V times C2, because this is just addition in the field and this is just multiplication over the field. Okay, in the field rather. Okay, and then what we can do is we can apply commutativity of multiplication here to rewrite this as C1 times V, so I've swapped C1 and V round, and C2 times V, okay, which is exactly what I wanted to prove this over here. Okay, so I've turned this thing into this thing. Okay, right, so indeed that property is also going to be true. Right, so a field is a vector space over itself if you just let the addition law be the addition of the vectors, and then the multiplication law represents scalar multiplication. However, that's not obviously a very interesting example, so what I now want to show you is how to construct some more interesting vector spaces over the field capital F. Okay, so what we're now going to construct is the vector space capital F superscript little n. Okay, and little n is allowed to be any natural number. It's allowed to be any positive integer. Okay, so we're going to construct this new vector space over the field capital F, which is going to be called f to the power of n. Okay, and n can be any natural number, and you'll get different vector spaces over this field for the different natural numbers. So you could construct f1, okay, which will be the same as what we've just seen. You can construct f2, f3, f4, f5, f6, etc. Okay, and this is going to be very much so analogous. In fact, it's going to be exactly the same as things like R2 and R3 that we've seen in classical algebra. Okay, so these are vector spaces over the real numbers. Okay, and now we're just generalizing this sort of concept. We are firstly, the first generalization is we've gone to an abstract field here rather than just the real numbers, and the second generalization is we're letting the power that we're going to do be any natural number rather than just 2 or 3. Okay, right, so let me show you how we're actually going to construct then this vector space Fn, okay, which is going to be a vector space over the field capital F. Okay, well, starting off, where do we start if we want to build a vector space? Well, the place we need to start is by constructing the set of vectors, okay? Then we need to define addition and then scalar multiplication by the elements of the field. Okay, so we'll start by constructing the set of symbols, the set of vectors, okay? And the way that you do this is you take arrangements of little n elements of the field, basically. So the set that is going to underlie this vector space Fn is going to be all n tuples of elements from the field capital F. So I'll denote this like so. x1, x2, all the way up to x little n here. So you'll have a little n elements from the field. All of these are from the field. xi are all elements from the field capital F. Okay, so this is what's known as an n tuple. I'll just write that down. So we've got n places basically, and all of them are allowed to take on any element of the field. So we'd call this an n tuple of elements from our field. Okay, I'll just colour this in here. Okay, now we have put all of these n elements of the field in a nice row here. Okay, we could have put them in a column, so I could have also had it arranged like this: x1, x2, and then we could have gone all the way down to xn. That's a little bit more bulky to write out, so we will use this row arrangement for now. Okay, but you could use the column arrangement if you like. At the moment, these two different arrangements are just different ways of doing it. They're different symbols. There's no more meaning in it at this stage. Okay, right. So we will use row vectors here rather than the column vectors. Okay, so we'll use the row arrangement. Okay, so here then is the set that is going to form our vector space Fn. We're going to take all of these row vectors which have n elements from the field, and you can let each one of these places vary over the entire field. Okay, so absolutely any combination of elements of the field that you want, basically, you're allowed to create them all, and I want you to create them all and stick them into this set. And that's the set then that I'm going to create to use as a vector space over the field capital F. Okay, so we've got the set then, so that's a good start. What we now want to do then is define an abelian group operation on this, which is going to be our addition operation. Okay, so let me go over the page and now we'll define addition. So I'm now going to define how to add any of these two symbols together. Okay, so I'm now going to take two arbitrary vectors from this great big set that I've constructed, which I'm getting a little bit ahead of myself calling them vectors because I haven't shown that it's going to be a vector space yet, but we are going to turn it into a vector space, so we might as well call them vectors. Okay, so I'm going to take one vector which I'll call v here, okay, and let's say that it's got components x1, x2, all the way up to xn, where all of these entries are from the field capital F. And we'll also have another vector which we'll call v bar, which will have components x bar 1, x bar 2, and I should probably say I'm relying again on you knowing the nomenclature components from your understanding of classical algebra, but the entries from the field in the vector are called the components. Okay, so this is x bar 1, x bar 2, all the way up to x bar n here. Okay, so let's colour them in. So I have v here coloured in red. Okay, and we'll have v bar here coloured in orange. Okay, right, so now what I'm going to do is define how to add these two symbols together. How am I going to add v to v bar? Okay, and it's just done using the intuitive way, okay, but I'll just colour this in. This is addition in the vector space. Okay, so I'm about to define this addition, and the way that you're going to do it is you're just going to add the components using the field addition. So the answer to this is going to be x1 plus x bar 1, where this addition is addition in the field. Okay, so these are both elements of the field, so you can add them together in the field. Okay, so you add x1 to x bar 1, you add x2 to x bar 2. Okay, again, that's an addition in the field, so I'll colour it in red here. Okay, and then you'll go all the way up to xn, which you'll add to x bar n. Okay, and again, that's going to be addition in the field here. Okay, and that will create you a new vector. Okay, it will create you something else which is in the set Fn. Okay, because all of these answers, all of these components of this new vector that you've created, they will all be elements of the field, because when you add two elements of the field together, you get another element of the field. Okay, so we'll get elements of the field in all n of these slots, and therefore this will be one of the elements of our set Fn, basically. Okay, right, so what we now want to do is make sure that this addition rule that we then have defined on this set of n tuples of elements of the field, that actually is going to obey the axioms of being an abelian group. And when I said earlier in this video that I wasn't going to go through the axioms of an abelian group now because we would see them anyway later on, now is the point that we're actually going to see the axioms of an abelian group if you aren't totally on top of them. Okay, so I'll remind you of them now. So axiom number 1 is closure, so that says that when we add two vectors together, so take any two vectors you like, v and v bar, from the vector space Fn, it must be the case that when you add them together, that the answer is still an element of Fn. Well, I've just said that. I've just said that when you add these two vectors together, you will always end up with another element of f to the power of n, okay? Because when you add the components together, you'll always end up with another element of the field. So all of these answers that we're getting here that are the entries in the n tuple, they will all be elements of the field. Okay, so indeed we will get another element that's in our original set, Fn. Okay, axiom number 2 then of an abelian group is associativity. Okay, so this says that if we have three vectors, so let's say we've got v, v bar, and v double bar, okay, which are all elements of Fn, we want to prove that when we add these three together, that there's one and only one answer as to what that actually is. Okay, so if we consider v plus v bar plus v double bar, we want there to be one and only one answer. Now, why might there be two answers to that? Well, because when you consider how to actually do this, you can't add three things together. Okay, you have to add two things together at once, and then so you have to break it down basically into just the addition of two things at once. So you can either put the brackets around v and v bar here, so that this says firstly add v to v bar, take the answer and then add it to v double bar, or you could put the brackets around v bar and v double bar, so you could make this v plus v bar plus v double bar, like so. Okay, and basically associativity insists that these two things, these two different ways of doing it, must give the exact same answer. Okay, so we want to make sure that our definition of addition is actually going to obey this. Okay, so once again we'll use the same sort of notation, so we'll use v is equal to x1, x2 all the way up to xn, we'll have v bar as x1 bar, x2 bar all the way up to xn bar, and we'll let v double bar be x1 double bar, x2 double bar all the way up to xn double bar. So let's now explore what the left hand side here would actually be. So if we're firstly adding v to v bar, what would that give us? That would give us the vector of the form x1 plus x1 bar, x2 plus x2 bar, and then you'd go all the way on till xn plus xn bar. Okay, so that's the answer to v plus v bar, just using the Weil definition. So I'll just highlight this up. So this portion that's in brackets here, this is the answer. And what we now want to do is add this to v double bar, which I'm going to write out for you. It's x1 double bar, x2 double bar, all the way up to xn double bar. So here is that vector. And now if we want to add these two together, again what we'll do is just use the definition here. So we'll add this component here to this component, this one to this one, and so on. Okay, so what we'll end up with is x1 plus x1 bar. Okay, the answer to that plus x double bar 1, or x1 double bar rather. Okay, then as our second component we'll get x2 plus x2 bar, and I'll just move this up a little bit. Okay, plus x double bar, x2 double bar. And I want to stress the reason that I've put brackets around these bits, because remember we do this addition first and then we add this additional component on. So that's why there's brackets around these portions. Okay, and remember that these additions here are all done in the field. Okay, so these are all additions in the field. Okay, and then this will go all the way up to we have xn plus xn bar plus xn double bar here. Okay, like so. And again, we firstly add those two together and then finally add that one on the side. Okay, so hopefully you can see that if we were to do this other way round, all we'd get is we'd get the same answer, but the brackets will be in a different place. Okay, so let me highlight this up. So when we do it this way, and I'll colour it in a different colour, so let's have it in an orange rather than red. When we do it this way here, we get the brackets like so. In each of these components, the brackets are around the unbar plus the barred bit. Okay? Whereas if we did it this way round, which I will denote in yellow here, we would get the brackets around the bar and the double bar, like so. So don't make me write out this one, because it does take quite a bit of time, but hopefully you can see that if we did it this way, that's what we'd get. We'd get the brackets in the yellow positions rather than the orange positions for each of these components. Now, because addition of elements of the field obeys associativity, it doesn't matter whether the brackets are in the orange position or whether they're in the yellow position. The answers are still the same, so that means that the entries are all going to be identical, basically. So these two vectors that you get here are truly going to be equal to one another. Okay, so that's why addition of the vectors in this way is going to obey associativity. Okay, right. So now let's go on to axiom number 3 of an abelian group and make sure that our way of adding together two vectors is going to obey that. Okay, so axiom number 3 says that there must be an identity in our vector space. There must be some vector which, if we add it to any other vector, we get that other vector back again. Okay, now the additive identity, the 0 vector in our vector space, is going to be the vector that has the additive identity from the field in all of its entries. Okay, so it's going to be 0, 0, and then all the way up till the nth entry here, 0. Okay, so this is going to be our 0 vector, our additive identity in the vector space. And the reason is, if we add this to any other vector, okay, so let's take x1, x2, all the way up to xn here. If we add these two vectors together, again we'll do it component-wise, so we'll add 0 to x1, we'll add 0 to x2, we'll add 0 to xn, and of course those additions are in the field, but 0 is the additive identity in the field, so we'll get all of the same entries here back again. Okay, so the answer will just equal x1, x2, all the way up to xn, i.e. it won't have changed this vector at all, basically, because we're just adding 0 to all of the components here in the field. Okay, and you can do that either way round, so you can have the vector on the other side and the 0 vector here. It doesn't matter. Either way round, you'll get that if you add a vector to the 0 vector, this vector where we've got 0 in all of those components, that will leave the vector unchanged. So indeed, this is the additive identity in our vector space. Okay, right, so I think we'll have a break here, and in the next video we'll complete this discussion of how addition is actually going to obey the axioms of an abelian group, and then what we'll do is move on to define scalar multiplication.